So this research is also about an environmental engineering aspect, environmental science aspect, and using Bayesian network for modeling PFAS contamination in private water wells in North Carolina. And my talk, I will first describe what PFAS is. You may heard or may not. I will describe that, and then the PFAS in private water wells in North Carolina and many other parts of the world, the objective of our research, the methodology that we use, and the result, and finally the conclusion. So PFAS stands for per and polyfluoroalkyl substances. This group of substances we have used long time, like for 60 years, in different material, and we are still using different form of that, specifically in carpets, for example. In firefighting, we have used the foam, and as you can see, many material around us are based on PFAS. And it's generally speaking is a exchange factors of carbon atoms and fluorine, which is usually pretty robust kind of combination, and for that reason it's called forever chemicals, because it's really hard to break down this type of chemical in the environment. And the bad news is that right now there are 5,100 of them all around us in our environment. So after we dispose those material in different areas, it ended up reaching to our waters and then to private wells or any other water source. For example, we have right now issues for surface water in Wilmington, North Carolina, because the river that we are using are contaminated. And PFAS has lots of problem. It can cause lots of problem for different ages. And you can see here those problems: increase in blood cholesterol level, or for pregnant women, like decrease the body response to vaccine, or decrease the fertility in women. For kids, the lower infants' birth rate. So it's really causing problem in different ages for us. And also, as I just mentioned, there are 5,100 of them. So even if environmentalists and toxicologists are trying to take care of like a group of them, there's lots of them that is still are outside, and we don't know what's the effect of those. So this map is actually showing the scale of that PFAS problem in the US, and specifically in any military sites around the US we have that issue, because they're using that for firefighting foam all around those, for training in those sites, for in airplane, like in different fire station they use PFAS for a long time ago, and it's a huge issue in the US, but not in just the US. In Australia I found this now as well, that they also really involved in this challenge. In Canada we have, in Europe we have, and probably in many other countries PFAS is a big issue. So now I'm going back to the study that I'm doing right now in the North Carolina as an example of how to use Bayesian network for modeling and get a conclusion, get a better understanding of the issue. So North Carolina, we are right now in here. The area that I'm going to present is in this region. And this is a watershed map for the North Carolina area. And the Cape Fear River watershed is the longest watershed in the North Carolina. And there is a chemical factory in that area that used this type of chemical for years. So we have received a data set from North Carolina Department of Environmental Quality that contains some measurement for wells all around that region, for private wells. And based on that, we have seen like 23% are above health goals of 140 nanogram per liter. and then 23% are undetected, and there's wide range of houses in between 0 to 140 nanogram per liter. The complexity arises when we can see there is a region, for example here, that we have like different houses, just one very exposed, the other one in the neighborhood not exposed. And so that like causes lots of issues, how we address those kind of regions. So we try to use Bayesian network here by adding dataset and find that complexity and solve that. So the objective of this research in general is to uncover those factors that influencing the PFAS contamination, and then why we try to determine why some wells are contaminated and others are not contaminated. And then we try to prioritize those regions that we want to do some remediation or testing based on our result. And then we also use the web simulator to develop a user-friendly website format for public people in the long run so they can also test their wells. Okay, so a private well, as you can see here, there's like combination of lots of data can be attributed to the quality of that. If the contamination is coming from the surface side, for example, vegetation is important, the characterization of the soil all the way down is important, the vegetation, the tree coverage are important, even that pipe, for example, to the house are important, the house age, the well age, the well depth is important. So all of those parameters are independently available from different sources. So we try to collect them and put it in our BayesiaLab. So for each well in the region, we know that tons of information regarding the parameters around that well. For example, we first received that data set, then we added like land coverage data set, soil survey data set. There are some waste site around that and some landfill around that area, so we try to find those wells that are close to those waste sites. We use air deposition model that we received from another research group that is based on the steady state air modeling, and we use that as well, and you can see tons of other data. So we ended up like 240 potential variables for each well in each location, and based on that we develop the machine learning with BayesiaLab software. So it's hard to figure out what's going on with the data set in general, so we use clustering method that is available in the tools, and based on that we like develop this like Chinese hat that Dr. Geoff mentioning in the advanced course, and we find those factors that are influencing a subgroup of variables, and then use that for our model. So our modeling goal is to have a classifier that can say a house, a specific house is above or below 140 nanogram per liter, which is the health goal, and then find those variables. And then we use this step like unsupervised learning and variable clustering to find out or to reduce the size of our data, and then eliminate the unrelated variable, and then use supervised learning. We usually use augmented naive Bayes algorithm for building the supervised learning. And we use a RAG curve, as Dr. McDonald Gibson also described, for our performance metric. And we try to have area closer to 100%. Yeah. And we also use cross-validation for our modeling to see if the model is responding in different conditions. We use 10-fold cross-validation, although this picture is describing 5-fold cross-validation. Okay, so based on the data set that we have, the first model is like get rid of almost 200 variables and just said that these 4 variables are important, like air deposition are important, distance from that chemical factor is important, average soil pH is important, and also the cation exchange capacity of soil is important. I'm going to describe the effect of those in the next slide. And this is also the mutual information with the Genx as a target node, and you can see those variables, air deposition and distance out of first and second one. So air deposition, as I mentioned, is a work of another researcher, and we use the data set is a steady state model for 2017 that they developed for that region, and we use that as an input in our variable. So it's clearly showing that when the deposition of air material, which is the unit is microgram per square meter per second, when we have higher that variable, we have higher risk, which makes sense generally. The other one is the distance from that factories. When we are closer, we have higher risk. We added additional variable like proximity to river, for example, so we just don't assume at the beginning that that factory is going to be the main source of problem. We also consider if the rivers, which is a big river in that region, also bringing contamination for our wells. We also added, as I mentioned before, we added proximity to a landfill in the region as a variable. So all of those show here that nope, those are not important, just this factory is important. And then the cation exchange capacity is another one that we also added. So this one is kind of changing. We have lower Genx when like we have lower cation exchange capacity, and then in the middle we have higher, and then again lower. And the same for here for soil pH. That's also another variable that we added to model and find out that how it's behaved the Genx measurement. Okay. So for a small portion of that data set, we have well depths and years of construction. So we decided also to run another model for that small portion, because in the general data set, that a small portion of data like well depths and years of construction is not showing up in our model. So we kind of separate those out, and like for 25%, we consider that, and we found out, yes, those like well depths is also important. Even well age is also important to some extent. And so well depths turn out to be actually really a good indicator. And if we have a well depth like more than 170 feet, we are going to have a really low risk. And the risk of Genx is usually it's usually happen more in those wells with shallower depths. Well age is also to some extent is important. So it's kind of strange, but I assume that because those older well, they are usually used digging or boring, and they don't have technology back. So the depths of those wells is also shallower. So that talk with the same like language with the first one, well depths and well age is kind of talking the same. If we have older well, they have also higher Genx stress. So all of this like model that I show like bring us to this picture that okay, for this region we will have this issue that there is a factories that producing chemicals. It go through air and by rain it come to ground, and then passing through the soil and reach to the well house, which kind of confirm a hypothesis that we have in that region. So that's one way to solve an engineering problem. And instead of going through the like testing and different things, we just use data and confirm a hypothesis to some extent. And then we also can produce like this type of special map that's showing, okay, if you want to do remediation, you can start this region or this region. There's no need to do some action in other regions. So like we can have this type of map as well, which show the risk of Genx in the long run. And the model performance is also like pretty good and reasonable. We have around like 82.7 K tenfold rock curve index, which is pretty good, although we always have a trade-off, but this is a good result for us. And the tornado graph also showing that which parameters are important. So as I mentioned, air deposition and distance from Chemours are important. For the other model, we have a little bit better performance, like 84 0.6. That was a result of that smaller data set, so that also we are seeing here the tornado graph for that data set. And we have this cool possibility because of BayesiaLab that we can develop these tools, and then people can put their data set and find out if they are at risk. So I developed 2 models based on that. Okay, so that was the one application of using BayesiaLab in environmental science and engineering and public health, as I described, but it can be used for any other contamination. And in conclusion, we found out what's the parameters that affecting or contamination for Genx in that region, and then the accuracy of the model. And if we have more data, like the second model that I show, we will have higher accuracy. And the main takeaways, although we have this PFAS is pretty complicated issues that we are facing, but by data and using this kind of tool, we can address that and we can tackle that problem to some extent, at least, or we can have a start point that use that for studies. So the accuracy of model is good enough for us to start. And I would like to acknowledge the funding source for this project from North Carolina Policy Collaboratory, and also the collaborator for this project is kind of combination of different universities, NC State and UNC, and the organization that help us collecting the data. With that, I would like, if you have any questions.